So this is our relativities from a random drop-off film plastic waste bag sorted out into the polyolefins that float. And this is your HDPE fresh apple bag that you draw off a roll for your apples. It's LDPE, which is your bread bag, frozen pea bag, frozen ice bag, and it's your polypropylene, which is your biscuit wrapper and biscuit tray. And then the sinking fraction, that's largely PET, which is your punnet of raspberries and strawberries, your meat tray, and obviously your soft drink bottle. And then you've got PVC in there, which was a little bit strange, but that's a tablecloth, disposable tablecloth. And then you've got modified atmosphere packaging. There's more and more of this. And what you perhaps want to do in looking at packaging, adding to the traditional hierarchy of reduce, reuse, recycle, is simplify. The more simple the polymers are that you use, the easier it is to have a circular economy, and the polyolefins are excellent for that purpose. So we perhaps want to see some simplification, this green bag moving over a little bit closer into the red bag area. And then the red bag area, it's really enabling more affordable food for more people. It is really, really functional packaging. But you want to interrogate it and say, look, is it really necessary? Is there a far simpler packaging format that we can use? But if we have to use things like modified atmosphere packaging, let's give them a specific gravity greater than 1. So we've got a really simple method to separate the two using a chemical which is really, really safe, which is called water. We want to reuse our water, but it's a very simple method that millions of tons of plastic film separation can be accomplished at an industrial scale, which is where we really need to get to. So here are our numbers by weight of what was inside that random drop-off plastic bag. And the largest one is LDPE, your bread bag. The large green bag that contained all of our plastic was pretty close to 10% of the weight of the LDPE that was in there. So it's interesting to ask, where does that liner bag come from? Is it made from recycled Australian plastic? Because it will have a huge effect if it actually is, if we can turn our old bread bags just into these liner bags and use thousands of them. The next one was polypropylene, your chip packet, your biscuit wrapper. HDPE was your fresh fruit and vegetable bag on a roll, and LLDPE is your cling wrap. And that was, by weight, about 2/3 of what was actually in the bag. And our Water for Little Fish shows that all of that floats. About 1/3 of the material sinks, and the biggest component of that is your modified atmosphere packaging. One of the things you have to ask yourself is, if you're worried about the Great Pacific Garbage Patch of floating plastic in the ocean, what about the 1/3 that doesn't float, that's sitting under the water, most of it off the coast of Southeast Asia and China? But with the map, the next component was PET, which is your punnet of strawberries. More commonly, it's your soft drink bottle. So people have thrown it in there. It's not film, but certainly it's in there, and we have to account for it. PVC, which is a strange one. It's not a very common thing in food packaging. It's very, very common as medical plastic. Hospitals are full of PVC. It's a very functional, hygienic, safe material. The curtain siders of the semi-trailers and trucks that you see on the road, and the billboards that you see outside real estate advertising boards. There's a huge amount of this material in the country, but it's not in the food packaging. But here we've got a lump of it as a tablecloth, and we have to account for it. Your bioplastics, these are coming along. They're quite expensive. You have to ask yourself, do you want a cup of coffee for $5 or $50? Because the bioplastics can be quite expensive. They're getting cheaper, and there's more of it coming in, and we have to account for it. As much as your paper's in there, and that's your paper dockets, your paper labels that are all over your punnet and all over your bags. So the grand total was 2.6 kilogram, and that's kind of what it looks like. Your green is the stuff that floats, your yellow is the stuff that sinks. So using water is a wonderful method of actually separating these, understanding that all of these in a chemical sense are very, very closely related cousins, that chemical recycling of polyolefins offers a pathway to actually turn all of these back into brand new plastic or diesel or hydrogen. So where there's millions of tonnes going to landfill, 2/3 of it actually is very, very amenable to a plastic circular economy. And then the MAP is starting to edge in a quite significant way, because it's very, very functional in terms of what it does. But perhaps if we could simplify and use more polyolefin, and if you are going to use MAP, either make it a floating fraction that is chemically compatible with your polyolefins, or a sinking fraction, so we've got a chance to actually separate it out from this quantity of sinking material. Some of the other things to consider with the whole, I guess, plastics recycling equation is the reverse logistics. How do you get plastic from Perth or Darwin into Melbourne? Because setting up a scale, plastics to hydrogen facility, it costs a lot of money. It's more capital conservative to set up one huge plant and bring the plastic in, rather than a plant in every city. And that relates to reverse logistics costs. So we had 2.6 kilogram in a large fluffy bag that took up one pallet space. So to transport that would cost us $38.46 per kilogram. But if we compressed it into a bale, and that bale weighed 1,000 kilograms, then there's a dramatic difference in the reverse logistics costs that makes it very, very viable to actually pick up this material from Perth and Darwin and bring it into Melbourne. But a baler that can do that might cost $500,000. And this is the problem in the recycling industry, lack of capital to actually get the productivity benefits. So the capital is required to look at efficient reverse logistics. It might be that you set up a $500,000 baler in each capital city to allow low-cost reverse logistics. And then if you do have a solution for turning the plastic into either recycled plastic or hydrogen, then capital is required to scale that up. Because for this 2.6 kilogram, it's actually taken me 2 days to hand sort it. And given that I'm not paid that much money, it's still very, very expensive kilograms as hand sorted material. If you've got a mechanical process that runs at 1 tonne an hour, that's far cheaper. If you've got a mechanical process that runs at 100 tonnes an hour, that's very, very much cheaper. So where Australia is at the moment is that we have really zero infrastructure to do any of this. We've been sending this material overseas with what I call thoughts and prayers recycling. We really haven't known what's happened to it. And China and Southeast Asia have let the boom gate down. It's no longer possible. We've sort of got to build genuine, auditable, transparent recycling infrastructure from pretty much where it is now at the moment, which is hand sorting, to scaling, and capital is desperately required to do that as quickly as possible. So having found a way to separate this material, it's pointless unless there's actually an end use for them. So what are some of the things that we can do immediately given will and capital? And what are some of the things that might take a little bit longer to achieve with these, to get these millions of tons of plastic actually more circular, a circular economy in plastics? So we start off with our polyolefins, our polys, and we've got a reasonably representative proportion of what's in landfill. It's LDPE, it's polypropylene, your bread bag, your biscuit wrapper. And then some of the issues with that, you could obviously recycle that material back into recycled plastic. You just having separated all these other things that frustrate the recycling of it into a plastic product, you form a recycled poly-based plastic. And some of the issues are there, the melt flow index, so very low MFI for your bread bag, very high MFI for your biscuit wrapper, polypropylene sort of injection molded products. And you're sort of mixing them together, 2/3, 1/3, and you're kind of mixing your melt flow index together. So you get this base material which may have sort of an average melt flow index. So you've got to design products for that melt flow index. You've got to get some bright students and product developers to say, look, we're going to give you 100,000 tons of this poly base. It's going to have an average melt flow index of about 20. It's all different mixed colors. It's going to come as sort of a khaki green, or what the industry calls jazz. Go and develop some products with it. Now, there's products we use today, which, for example, are garbage bags, builder's film that goes underneath concrete when you pour concrete. Very simple products like that certainly could be scaled up in their application if people knew that Australian waste could be turned into Australian manufactured things like garbage bags and builders films, and these weren't terribly expensive, and certainly helped resolve and start the journey now on what we do with this plastic. And we do use millions of garbage bags in Australia every year, and a lot of them are imported, and they're imported from systems that create huge amount of water pollution. For every ton of plastic which is processed, 10 tons of wastewater is created, and that's really why China shut down the import of these waste materials. So really, really cheap imported bags represent a huge water pollution problem overseas. So it is possible to make these things in Australia and be cost competitive without creating water pollution. And we can do that now. Over the next 1 to 3 years, simply by pulling out all of these from this material, you've got a great feedstock using pyrolysis to turn your polys into diesel. There's still a lot of tractors and freight trucks and ships and transport which depend on diesel. All of our diesel is imported. So for domestic fuel security, instead of throwing millions of tons into the environment, you could very, very quickly turn it into diesel using very, very established pyrolysis technology. It's just a matter of scale and capital to make that happen. I guess far more sophisticated conversion is turning your polyethylene into its components, and one of those is ethylene gas, which is the base product that creates brand new polyethylene. So that really resolves the question of everything being the one colour, being able to take all of those mixed colours and turn them into a virgin grade polyethylene that's clear and can become any colour and is safe for food contact. Because this recycled material here, you don't actually know whether the old bag has contained rat poison or some weird chemical. Very, very unsafe perhaps to put that into food contact, but this system here can create virgin-like material that is safe for food contact. Now that process doesn't just create ethylene gas, it can create CO2 emissions, it can create carbon, it creates char. There's a lot to be worked out, and building scale infrastructure like this, you're talking about multi millions of dollars. But we do have a refining capacity in Australia, particularly in Melbourne, around Altona and Geelong, that can be adapted to it. So things that would normally take decades to do are already here. It's just a matter of applying capital to create a scale solution where really we've got millions of tonnes to deal with. But this would be a very, very circular model. The genuine recycling of a tonne of plastic, getting it out of the environment. It doesn't quite create a tonne of virgin plastic, but it is a very circular and very sustainable model. Scale and the capital applied to it will determine how expensive this chemically recycled polyethylene is. So certainly we hope for scale to make it cost competitive with virgin polyethylene formed from crude oil. Another very exciting possibility is polys to hydrogen, where you've removed all of these sorts of things. You have a wonderful feedstock to actually start looking at the extraction of hydrogen, because this poly is a combination of hydrogen and carbon. We're liberating the hydrogen out of it, and then ideally we're creating solid carbon, not CO2 emissions. So some very exciting technology that's developing. If you really were serious about it, you could create a domestic scale hydrogen industry based on converting a waste material that's polluting the environment into a zero emissions transport fuel, if you can manage the emissions in this process here. So that's the tension between CO2 or carbon, but very, very possible in that time frame. We look at these ones here, and one of the things that we've done is we've introduced water. So this material is wet. Some processes will require us to dry it, but where it is wet, one of the interesting things that's coming up, particularly with PET, nylon type material, is enzymatic conversion. So with PET right now, you can recycle old PET into new PET, but your soft drink bottle might be clear, but there's other PET out there that isn't, it's coloured. So invariably, like the Jazz or khaki poly recycled plastic, that sometimes ends up as black. It's very difficult to get clear PET out of that system. It is possible, and it's already happening, but very promising technology in the 1 to 3 year time frame in terms of commercializing and scaling up is enzymatic conversion. So like chemical recycling, you're breaking down the plastic into its component parts and then recombining them to form brand new PET. So a very good pathway. And that also has an influence in dealing with our MAP, where we've got nylon in there or various other polymers that are amenable to enzymatic conversion. It's part of the solution to MAP. Another solution to MAP is actually aluminium recovery. So is it aluminium or is it plastic in the dog food bag? And you could use the plastic in that dog food bag as the energy source to melt and recover the aluminium in a pyrolysis process. It's worth having a conversation around MAP, around the question of simplifying. Does it really need to be MAP? Can we make it out of a far simpler polyolefin? And then if we can't, because we're getting fantastic, affordable food for more people, create some basic rules around it, like having a specific gravity of greater than 1, so we can actually separate it from the larger, quantity of plastic out there using a very simple method. Or if it actually does float on water, if it has a specific gravity less than 1, make sure it's compatible with your polys. So it's a conversation worth having now, as well as looking at some of these other opportunities around our MAP and our PET. PVC, the question now is reduce it in food applications, because it is quite complicated in this whole mix. But there's, tons of PVC out there, medical plastics, billboards, real estate hoardings. Somebody's got to set up a process to deal with this material. There's a lot of it out there. Your electrical piping, your plumbing piping is all PVC. It's not going away. It is actually quite a wonderful functional material. So can we add the little bits of PVC that we get out with recycled plumbing and electrical piping and curtain sides from trucks? Yes, we can. There is a chemical recycling process that basically dissolves the PVC and allows you to reform virgin grade PVC. So somebody ought to set up that infrastructure over the next 2 to 5 year time frame. With our bioplastics that are compostable, our paper that's in there, our food residues that are in there, what we can do now is compost it. If we're recovering these components from the water as a sludge, it is amenable to composting, and we can certainly set that up now. So it's not as if there are no solutions. There are solutions that exist today, but they need capital to be scaled up.
2, 1.
So how do we know so much about plastic? Well, Lainey, what do?
We do recycle plastic, cardboards, and also pastel food. So what we do over here, we separate plastic, we separate cardboard, and we also do production with our food, with our bread.
So the main thing is that we get lots of packaged food. And the food, it just all comes in plastic. Paper, but mainly plastic. And we've never been able to find anyone that could help us with this plastic because it comes with food contamination. All the issues that we've gone through are so frustrating with plastics recycling. So we've been doing food recycling for over 20 years. We've done hundreds of thousands of tons of food recycling. We know how to make recycling work and not work. And then we've gone and built a plastics recycling process that accepts that the plastic that we get is all different types of plastics mixed together, plastics mixed with things that aren't plastic like paper and foil and food and dirt. That's the way the plastic comes. So we welcome you to have a look at this process and come on the journey to getting the rest of the plastic out there recycled. The plastics that we recover from the food that we recycle, we turn back into crate liners for more food waste. So we've set up a circular economy in film plastic where old bread bags are turned into crate liners for containing food production waste that comes back to us, and then we recycle the crate liners again. So we want to extend this principle of a plastics circular economy out into the wider world, and we'd be grateful for your help to scale it up.